Hey guys, Professor Doney again. We're in the middle of talking about launch problems or throw-up problems, and we allow time to go on enough that they come back down, assuming we don't throw it so hard or launch it so hard that it leaves the Earth's gravitational pull. But we're staying close to the surface, so anything we throw up, we assume it's going to come back down. So we're going to do a second problem, just because I think the last one I did maybe wasn't in depth or clear enough. We have our equations over here, and we're going to launch this object at 30 meters per second. Now, what we expect to happen is the object's going to go up, it's going to reach its peak, and it's going to come back down and hit the ground. Okay. At the peak, again, as we said before, its velocity at the peak will go to 0. So on the way up, that would be a final velocity, and on the way down, that would actually be our initial velocity. Okay. If we find out how high it goes up, we're going to call that y up, which is the same thing as its maximum height or the height of the peak. We're still picking gravity as downward, so we have to adjust that in the equations when we need to include that. Alright, so let's go through and find out. We're going to find the time up. That's from the first equation. Final velocity 0 at the peak, plus 30 here, plus minus 9.8, because gravity is pointing down, and we're calling positive upwards. Now, if you get a negative time, it just means you missed that mistake. You have the minus sign. It implies we went back in time, which we can't do, at least not right now. Anyway, this comes out to be pretty much 3 seconds, maybe a little hair over. I'm going to keep it at 3 seconds for easy numbers. All right, let's find out how far it goes up. Now, we could use the second equation just for something different, 2g delta y. Again, still positive up. Change colors here just to give us something different view. And final velocity 0 squared, initial 30 squared, twice minus 9.8, and delta y. Alright, what that ends up being is delta y is minus 900 after we square the 30, divided by minus 19.6, and if my calculator is right here, that would be just shy of 46 meters, so let's call it 46 meters. Okay, 45.9 actually. Now what we're going to do is we're saying the object is now at its peak, and it's now going to fall back down to the ground. Now, how far does it fall? Well, it has to fall 46 meters. How long should it take? 3 seconds. But we're going to check that, okay? So at the peak, its velocity has gone to 0. So on the back part, we're going to treat this as a drop problem or a free fall problem and use its initial velocity as 0 because it already hit the peak and now it's on its way back down. So what we're going to do is do a drop problem real quickly here from that height. And we can use 45.9, so we're closer to accurate. That's 0 times time, half. Gravity is a positive 9.8 because we're moving downwards, and gravity is also downwards. That ends up being t equals the square root of 45.9 divided by 4.9. And if I go through that and take the square roots, I get 3.06 seconds, which is exactly what we got here, but we were just calling it 3 seconds. So we verify that if it falls down the same distance that it went up under the influence of gravity, ignoring air resistance, the time up equals time down. And that's an important concept for looking at things that go up and come back down to the same spot when we launch them, throw them up, shoot them up. Anything is just given initial velocity and let to go on its way. So I hope that cleared up a little bit more. If we need to find out where it is beyond this 3 seconds or beforehand, we would just change our time, and back in here we can put a different time in. So hope that helped out. Next we're going to go and look at when we throw it up and it lands at a different height, whether above us or falls below us, and how we're going to look at those.